We are going to talk about electromagnetic waves in chapter 25, and we show that electric and magnetic fields can work together to create traveling waves called electromagnetic waves, or just to write them in short form, ENM waves. Now, these waves are responsible for everything around us, from the very visible light to the infrared light to UV lights to X-rays to gamma rays and all the forms of light. When it comes to electromagnetic waves, the very big name in this field is James Clerk Maxwell, who said that because a changing magnetic field produces an electric field, which we called Faraday's law, a changing electric field should similarly produce a magnetic field. Now, Maxwell suggested a sort of symmetry that links electric and magnetic fields. You can go ahead and study page 881 and the top of the page of 882 to get a better idea of how electric field and magnetic field are working together to make an electromagnetic wave. But what we must mention here is the direction of propagation for electromagnetic waves. So if we have both electric fields and magnetic fields, what will be the direction of propagation for electromagnetic waves? So again, we're going to use the right-hand rule, but this time to find the direction of propagation. Now, if you look at the figure 25.4 on your book, the coordinate that the book is using is that this is the positive x, this is the positive y, and this is the positive z direction. So this is the coordinate. Now, to find the direction of propagation, point your fingers, the fingers of your right hand, in the direction of E. So your open fingers are in this direction, and this is your finger. And then curl your fingers toward B. So what you're going is that you're going to close or brush or curl your fingers to the direction of B. Now your thumb points to the direction of propagation. Alright, so the direction of propagation according to this coordinate is going to be in this direction. So this shows the direction of electromagnetic waves propagation. This is as much as you need to learn in this section. Now we need to move to section 2 to learn more of the calculations and the numbers that we are going to use for finding the electromagnetic waves directions. Okay, first things that is need to be said is that the electromagnetic waves, all of them, travel through a vacuum with precisely the same speed, which is the speed of light in vacuum, because light is a form of ENM wave. So this is, of course, you know that we show it by C, which is 3 times 10 to the power of 8 meters per second, and this is the speed of light in vacuum. And it's worth mentioning that the first scientific attempt to measure the speed of light was made by Galileo, who used 2 lanterns for the experiment. And of course, because we are studying a higher level of physics here, it's good to know that this speed is just an approximation, and we are going to use the approximation in our calculations. The next theory that we need to know is that Maxwell's theoretical description of electromagnetic waves allowed him to obtain a simple expression for C in terms of the previously known physical quantities. So what he found is that C equals to 1 over square root of epsilon naught mu naught. And if you remember, we use this epsilon naught and mu naught, the first one in the electric field and um, the second one in the magnetic fields. Okay, it's good to remind ourselves that epsilon naught is 8.85 times 10 to the power of negative 12 Coulomb square divided by Newton meter squared. And this occurs in the expression for the electric field due to a point charge, or in fact, the epsilon naught shows the strength of the electric field. And then we have constant mu naught, which is 4 pi times 10 to the power of negative 7 Tesla meter per amp, which plays an equivalent role for the magnetic field. Now, if you simply put these guys in this equation, you should get the same number for the speed of light in vacuum. If you remember from Physics 1, the section 6 in chapter 14 of this book discusses the Doppler effect for sound waves, that is the increase or decrease in frequency as a source of sound approaches or goes away from us. Now we have the similar effect that is applied to electromagnetic waves. However, there are two main differences here. First, sound waves require a medium through which to travel, whereas light can propagate across a vacuum. Now, the second difference is that the speed of sound is different for different observers. For example, an observer approaching a source of sound measures and increases the speed of sound, whereas an observer detecting sound from a moving source measures the usual speed of sound. Now, for this reason, the Doppler effect with sound is different for a moving observer than it is for a moving source. But in contrast, the speed of electromagnetic waves is independent of the motion of the source and observer, and we'll study more about this in future. So there is just one Doppler effect for electromagnetic waves, and it depends only on the relative speed between the observer and the source. Let's call u to be the relative speed that is small compared with the speed of light. And let's call f to be the frequency of the light source. Then we can define the observed frequency to be f times 1 plus and minus u divided by c. So these plus and minus signs are for two situations. The plus sign or the positive sign applies to a source that is approaching to the observer. So I put here approaching. So if the source is approaching to the observer, we're going to use the positive sign. But then if the source is receding from the observer, then we're going to use the negative sign. Another thing that we need to take care of is that u is a relative speed between the source and the observer, both of which may be moving. For example, if an observer is moving in the positive x direction with a speed of 5 meters per second, and a source ahead of the observer is moving in the same direction, in the positive x direction, with a speed of 12 meters per second. So this is the source, and this is the observer, right? Then the relative speed is 12 minus 5 meters per second, which is going to be 7 meters per second. Now, because the distance between the observer and the source is increasing with time, then we would choose the minus sign in f prime. Okay, let's solve one problem for the Doppler effect in electromagnetic waves. Exercise 25.4 on your book says that an FM radio station broadcasts at a frequency of 91.5 megahertz. If you drive your car toward the station at 26.1 meters per second, what change in frequency do you observe? Okay, like always, we first write the known and unknowns of the problem. So here, the frequency of the source, which is the radio station, is 91.5 megahertz, and you are the observer, and your frequency is going to be the unknown of the problem. And then the relative speed is 26.1 meters per second as given in the problem. Now let's go ahead and apply the equation that we had for Doppler effect. Okay, so the sign that we should choose here is the positive sign or the plus sign because the car is approaching the source. So to solve this problem, I can rearrange, and because finally we are going to look for the change in the frequency, so I can just write down this equation in this form. So f prime minus f, or the changes in frequency, is going to be f times the relative speed divided by the speed of light. So what I'm going to do here is I'm going to convert the megahertz to hertz by multiplying by 10 to the power of 6, and then times 26.1 meters per second divided by 3 times 10 to the power of 8 meters per second, and the change in frequency, this delta stands for change, is going to be 7.96 hertz. There is another example on your book 25.5 that I urge you to read yourself. But let's talk some about the electromagnetic spectrum, and this is page 889 on your book. Now, when white light passes through a prism, it spreads out into a rainbow of colors, with red on one end and then violet light on the other. In chapter 14, we have seen the relationship between frequency and wavelength for any wave with a speed v. That is, v equals to f lambda. V is the speed of light, f frequency, and lambda is the wavelength. Now, if we want to apply this for electromagnetic waves in vacuum, because they all have the speed c, I can write c equals to f lambda. Now, this is always a constant, so if the frequency increases, this means that the wavelength is decreasing. So for the shorter wavelength of light, we have more frequency and opposite. Okay, look at example 25.6. In this example, we want to find the frequency of red light with a wavelength of 700 nanometers and violet light with a wavelength of 400 nanometers. So I'm going to solve only one of them. So for the red light, for example, we know that the wavelength of red light is 700 nanometers. So this is the wavelength of the LED light of the problem. Now, what is its frequency? What is the frequency of red light? So what I need to do is that I can simply find the frequency by dividing C by lambda here. So I'm going to divide 3 times 10 to the power of 8 meters per second by 700 nanometers, which is 700 times 10 to the power of negative 9 meters. And then the frequency of red light is 4.29 times 10 to the power of 14 hertz. So the frequency of an electromagnetic wave can have any positive value, and this full range of frequencies is what we call the electromagnetic spectrum. Now, the certain bands of a spectrum are given special names because of the special properties that they have. Okay, it's good. If you take a look at figure 2512, the electromagnetic spectrum on your book, so that we can study some of the properties of these electromagnetic waves together. Starting with radio waves. So radio waves are the ones that in figure 2512 is um, way to the left of the spectrum. So here we are talking about 10 to the power of 6 hertz to 10 to the power of 9 hertz of frequency. Using the equation that you have, you can instantly find the wavelength to be between 300 meters to zero point 0.3 meters. So this is a very long wavelength. This is very important because of the radio and television waves stand in this range of frequency. Now, these waves that are having this range of frequency are produced in a variety of ways. For example, molecules and accelerated electrons in space give off radio waves, which radio astronomers detect with large dish receivers. These waves can be produced when a piece of adhesive tape is slowly peeled from a surface. Also, radio waves are being emitted by many astronomical objects and can be detected by radio telescopes. And a sample or one of the examples of the receivers of these radio waves can be seen in figure 2513. Okay, we are now moving to the right of the spectrum. Next in line are the microwaves. These waves have the frequency of 10 to the power of 9 to 10 to the power of 12 hertz. Now, as you can see, frequency is increasing, so the wavelength is decreasing. So the wavelength is going to be between 300 millimeters to 0.3 millimeters. Now, waves in this frequency range are used to carry telephone conversations, to operate the global positioning system, which is GPS, and to cook our food. Of course, we have all used the microwaves in our home. So what is important here is that GPS wave falls in this category. On the right side of microwaves, we have infrared waves with frequencies of 10 to the power of 12 hertz to 4.3 times 10 to the power of 14 hertz, which makes their wavelength to stand between 0.3 millimeters to 700 nanometers. So you can see that the wavelength is decreasing. So these are the electromagnetic waves with frequencies just below that of red light. So these waves can be felt as heat on our skin but cannot be seen with our eye. Now, many animals, including various types of pitwipes and mosquitoes, have the infrared receptors on their face that allow them to see the infrared rays that are given off by a warm-blooded prey animals, even in the total darkness. Now, the reason that some other animals do not have the infrared receptors is that simply because they don't need it, because they have other ways of seeing, so they have like better eyes, perhaps. And secondly, is that all the warm-blooded animals uh, they emit a lot of infrared waves themselves, so that will be interrupting the signals that they get from other animals. So we cannot be warm-blooded and emit infrared, yet we feel the infrared the way that the cold-blooded animals do. So what is important here is that we know, so here the animals have the infrared receptor. Another thing that if you look around you, you should be able to find is the remote controller. So if you have a remote controller near you, Just go ahead and take a look at it. You see that there is a red plastic spot on your control, and if you can find, there should be another place very similar to this red dot on your TV. So what happens is that when you push the remote controller button, it emits some infrared radiation, which will be received then by the electronics. Another good experiment is that we should know that humans, we can feel or we can detect infrared radiation somehow, not as good as mosquitoes can, but we still can do that. So if you want to test this, go ahead and close your eye and then try to bring your hand close to your cheek. So you can see that your face feels the warmth of your hand. So our infrared receptors are mainly in our face and on our lips. Okay, next we have the visible light, and this is the portion of electromagnetic spectrum that is most familiar to us because it is visible, of course. So all the colors that we see around us is lying in this very small portion of the electromagnetic spectrum. And I need to emphasize that if you take a look at the figure, it is a very small portion of the spectrum. Okay, for the frequencies that are above that of violet light in the visible spectrum, we call the electromagnetic waves to be ultraviolet light or UV. Now, these UV lights are mostly known for the probability of developing a skin cancer if they are shining at our skin. So, fortunately, most of the UV radiation that reaches the Earth from the sun is absorbed in the upper atmosphere, where we call the ozone layer. But not all the UV light is dangerous. We have used UV light for some good practices too. For example, it is a very good source of light to kill the bacteria in the surgery rooms, in the fume hood that we do the cell culture, or even in water. There are many rural regions of India that they use the UV lamp to purify their water. Okay, as the frequency of the electromagnetic waves is raised even higher, then it falls into the range between 10 to the power of 17 hertz and 10 to the power of 20 hertz. Now, this is called X-rays. The typical X-rays that we use are in medicine and in, for example, taking an image of our tooth or our bones, because the X-rays are absorbed in calcium, that is the majority of the component of the bones and teeth. And finally, we have the electromagnetic waves with frequencies above 10 to the power of 20 hertz, and we generally refer these electromagnetic waves to as gamma rays. Gamma rays I can even use by this symbol here. These are the waves that are even more energetic than X-rays, and they are often produced as neutrons and protons rearrange themselves within a nucleus, or when a particle collides with its antiparticle, and then the two of them annihilate each other. Now we are going to explain all these procedures of how to produce gamma rays and X-rays in chapter 32. But just know that because of the high energy they have, they're used to kill cancer cells and the microorganisms in food. So this will bring us to the end of lecture for today. Please let me know if you have any questions. You can email me or just make your questions on the discussion board that we have on Blackboard. And we will continue with section 4 in the near future. So take care of yourself and stay healthy.